Hello everybody. Today we will start to discuss problems from first round of US Physics Olympiad year 2010 F equal MA. Each year this round has 25 problems for which you have 75 minutes and you need to choose correct answers from 5 A, B, C, D, E, usually like this. Before we start, please subscribe for this channel. In this case, you will get all material for this US Olympiad problems and much more very good and very difficult problems. In this video, I will give you only problems. For solutions, I will give you a reference below. In that case, you have a chance to solve it yourself. So, first three problems. Questions 1 to 3 refer to the figure which is on the right, and they shows a representation of the motion of a squirrel as it runs in a straight line along the telephone wire. So first problem. If the graph is a graph of position versus time, then the squirrel has the greatest speed at what times or during what time intervals? That was the first question. Second problem. If instead the graph is a graph of velocity versus time, then the squirrel has the greatest speed at what times or during what time intervals? And problem number 3. If instead the graph is a graph of acceleration versus time and the squirrel starts from rest, then the squirrel has the greatest speed at what times or during what time interval? Solution. Solution for the first problem. If the graph is a graph of position versus time, then the squirrel has the greatest speed at what times or during what time interval. So if we have this graph as position versus time, and the greatest speed it has from B to D. It has a negative slope, but the speed is absolute value for velocity. So that's the correct answer, C, from B to D. Problem 2. If instead the graph is a graph of velocity versus time, then the squirrel has the greatest speed at what times or during what time intervals? So obviously greatest speed will be in points like maximum for these graphs or minimums for these graphs. That will be point B and D. B is positive and D is negative. So the correct answer is D. And problem number 3. If instead the graph is a graph of acceleration versus time and the squirrel starts from rest, then the squirrel has the greatest speed at what times or during what time interval? So when we have acceleration versus time, the speed could be found by integrating this area on the graph, and we see that we have a positive acceleration till point C, and it has the greatest area of this triangle from A to C, but after that area is going negative and speed is decreasing. So it means that correct answer is point C, where we have a positive area. That's it. We're done. Problem number 4. Solution for this problem you can find in a reference below this video in the description. Two teams of movers are lowering a piano from the window of a 10-floor apartment building. The rope breaks when the piano is 30 meters above the ground. The movers on the ground, alerted by the shouts of the movers above, first notice the piano when it is 14 meters above the ground. How long do they have to get out of the way before the piano hits the ground? Solution. Here we can use a regular formula which is connecting height and time for accelerating motion. So if we have height, we can count what is time. Now we can count time difference between whole 30 meters away and the other point which is 14 meters above the ground. So that will be these calculations. So we have delta t equal t2 minus t1, which is this expression for height 30 meters minus this expression for height 16 meters. And the final result is 0.66, which is answer A. Problem number 5. Solution for this problem you can find on the reference below this video in the description. Two projectiles are launched from a 35-meter ledge as shown in the diagram. One is launched from a 37-degree angle above the horizontal, and the other is launched from 37 degrees below the horizontal. Both of the launches are given the same initial speed of v0 equal 50 meters per second. The difference in the times of flight for these two projectiles, t1 minus t2, is closest to what? Solution. Of course, here we can use regular equations to find what is total time. In that case, we have to solve a quadratic equation for this trajectory. But here this shortcut. If you see in this projectile 1 trajectory we have 37 degrees above horizontal, but when this projectile reaches the same height 35 meters, that will go same 37 degrees but below horizontal with the same speed as for this projectile. So it means that projectile 2 and projectile 1 have the same conditions for motion from the same height, and they will spend the same time for that. It means that total time difference will be just motion from this point to this point. And now we can easily to count what is total time using this formula. This is just equal speed difference in a vertical direction, which is 2v0 sine theta divided by g, and total result is 5.6, around 5.6. That's between 5 and 6, but it's closer to C, so probably that's correct answer. Problem number 6. Solution for this problem you can find in the reference below this video in the description. So problem. A projectile is launched across flat ground at an angle theta to the horizontal and travels in the absence of air resistance. It rises to maximum height h and lands a horizontal distance r away. what is the ratio h over r? Solution. Here we can find what is the distance using this formula. Distance equal Vx multiplied by total time t, which is V0 cosine theta t. Now how to count time t? That's the formula. So total time to travel is a change of vertical part of velocity to Vy over acceleration g, which is 2V0 sine theta over g. Now we can substantiate this time t in this formula, and total range d will be this expression. Now we need to find what is total height. Using a well-known formula, total height equal v vertical square over 2g, which is V0 square sine square theta over 2g. And now, to find what is a ratio, we need to divide h over d, which is this expression, 1/4 from tangent theta. Correct answer is E. Problem number 7. Solution for this problem you can get from a reference below this video. Harry Potter is sitting 2.0 meters from the center of a merry-go-round when Draco Malfoy casts a spell that glues Harry in place and then makes the merry-go-round start spinning on its axis. Harry has a mass of 50 kg and can withstand 5g of acceleration before passing out. What is the magnitude of Harry's angular momentum when he passes out? Solution. So first we can write expressions for angular momentum. For point mass, that will be mr square multiplied by omega. And now we can count omega, because we know what is the maximum acceleration Harry Potter can withstand. That will be centripetal acceleration A equal 5g, which is r omega square. So from this formula we can count what is maximum omega. That will be this one. And after that we can insert this omega to the first formula and get the result. So that's the answer. Angular momentum equal mass multiplied by square root from 5 r cubed g, which is 1000 in SI system. So it means that the correct answer is D. Problem number 8. Solution for this problem you can find in the reference below of this video. A car attempts to accelerate up a hill at an angle theta to the horizontal. The coefficient of static friction between the tires and the hill is mu greater than tangent theta. What is the maximum acceleration the car can achieve in the direction upward along the hill? Neglect the rotational inertia of the wheels. Solution. Because coefficient of static friction is greater than tangent theta, it means that this car can accelerate up the hill, and maximum possible force of friction in that case equal to mu multiplied by normal force, which is mu mg multiplied by cosine theta. And downhill we have part of force of gravity, which is mg sine theta. So total equation for car motion will look like this. Here direction up the hill is positive, and after cancelling mass we have a result. Acceleration equal g multiplied by mu cosine theta minus sine theta, which is answer B. Problem number 9. Solution for this problem you can find below this video on the reference. A point object of mass m hangs from the ceiling of a car from a massless string of length L. It is observed to make an angle theta from the vertical as the car accelerates uniformly from rest. Find the acceleration of the car in terms of theta, mass, length, and g. So, solution. First, let's draw a free body diagram. We have two forces acting on this mass. That's a force of gravity, mg, which is going down, and tension from this string, which is going in the direction of this string. And let's write equations in vertical and horizontal directions. Vertical it's not moving, so it means that we have this equation that the force of gravity mg, that's exactly equal to tension multiplied by cosine theta. And horizontally we have this equation. We have ma equal tension multiplied by sine theta. Now we can just divide this second equation by first equation and find what is acceleration. This is the answer. A equal g tangent theta, which is a C, correct answer. Problem number 10. Solution for this problem you can find below this video in the reference. A block of mass m1 is on the top of a block of mass m2. The lower block is on the horizontal surface, and the rope can pull horizontally on the lower block. The coefficient of kinetic friction of all surfaces is mu. What is the resulting acceleration of the lower block if a force F is applied to the rope? Assume that F is sufficiently large so that the top block slips on the lower block. Solution. First, let's draw a free body diagram. In the horizontal direction, we have three forces acting on the lower block. That's a pulling force F and two forces of friction. Friction F1 between block 1 and 2, and friction F2 between block 2 and the surface. And now we can write equation for this motion. That will be this one. M2A2 equal force F minus first force of friction minus second force of friction, but first force of friction equal to mu multiplied by normal force between block 1 and 2, which is m1g. Second force of friction equal mu multiplied by normal force between second block and surface, and this normal force equal m1 plus m2g. So basically we have this the result, and finally to find what is the acceleration a2 we need to divide this equation by mass m2. That will be a result, and this is answer A. Problem number 11. Solution for this problem you can find below this video. The three masses shown in the accompanying diagram are equal. The pulleys are small the string is lightweight and friction is negligible. Assuming the system is in equilibrium, what is the ratio A over B? The figure is not drawn to scale. Solution. First, let's draw the system in equilibrium. Because there are no friction, the tension in the rope is the same everywhere. So it means that it's equal to mg. And now we see that because this tension equal mg, so this middle mass should be in equilibrium when we have this equation, that mg equal two tensions multiplied by cosine theta. That's theta, its angle between vertical and the direction for this string, so which is equal to mg cosine theta. From here we can find that cosine equal 1/2, and from this figure we can see that a over 2 divided by b, that's tangent theta. And because cosine, that's 1/2, theta equal pi over 3, and the tangent pi over 3 is equal square root from 3. And that means that a over b equal 2 square roots from 3, which is E, correct answer. Problem number 12. Solution for this problem you can find below this video in the reference. A ball with a mass m projected horizontally of the end of a table with an initial kinetic energy k. At the time t after it leaves the end of the table, it has kinetic energy 3k. What is t? Neglect higher resistance. Solution. First, let's write expression for initial kinetic energy. So k equal 1/2 mvx square. After time t, it has a kinetic energy 3 times k. It means that 3k equal 1/2 mvx square plus 1/2 mvy square, where vx is not changing, but vy equal gt. And after, when we cancel 1/2 mvx square because it's k, we have 1/2 mgt square equal 2k. From here, time equal 2 over g multiplied by square root from k over m. And this is answer B. Problem number 13. Solution for this problem you can find in the reference below this video. A ball of mass m and radius r has a moment of inertia I equal 2/5 mr square. The ball is released from rest and rolls down the ramp with no friction loss of energy. The ball is projected vertically upward of a ramp as shown in diagram. Reaching the maximum height y maximum above the point where it leaves the ramp determines the maximum height of the projectile y maximum in terms of h. Solution. In this problem the main key is that whole potential energy going for translational kinetic energy and rotational kinetic energy. And because there are no sliding here, we have always this relation when ball contact with the surface. Omega, which is angular speed, equal v over r. And it's equal to this expression even in the last point where this ball contact with the surface. So it means that before that potential energy going to translational rotational kinetic energy, and after that when ball reach this point, only translational kinetic energy going to potential energy, but rotational energy is still the same. It's not using for increasing height. So force of friction is not helping us to reach the highest point. And in that case we need to do next steps. So first, potential energy mgh equal 1/2 mv square, which is translational kinetic energy, plus 1/2 I omega square, which is rotational kinetic energy. Now using this expression and the expression for I, we can insert them here and find finally that mgh equal 7/10 mv square. This is how to find the v square in this point of losing contact. In this point v square equal 10/7 gh. And now we can do a reverse problem, so we can find how is this translational energy going to potential energy. So here we have this equation: mgy maximum equal 1/2 mv square, and after when we put this v square from here, we can find that that's equal to 5/7 mgh. So it means that y maximum equal 5/7 h, which is answer D. Problem number 14. Solution for this problem you can find in the reference below of this video. A block with mass m1 equal 5 kilograms, with the speed v0 equal 8 meters per second, travels 2 meters along a horizontal surface where it makes a head-on, perfectly elastic collision with the block of mass m2 equal 15 kg, which is at rest. The coefficient of kinetic friction between both blocks and the surface is μ equal 0.35. How far does the 15 kg block travel before coming to rest? Solution. So we need to split this problem for 3 parts. First part, it's we need to find what is the speed of the first block before collision when it travels 2 meters. Second part is to find what is the speed of second block after perfectly elastic collision. And third part is find what is the distance second block travel after this collision. Let's do it step by step. So first step, we have equation. So we have this equation, initial kinetic energy equal final kinetic energy minus work done by force of friction. So that will be this expression. And we can find what is v1 square from here. This expression. Now we have absolutely elastic collision of 2 blocks with mass m1 and m2, and this is a very well-known problem when one block is at rest and other is moving to it, and it has a perfect elastic collision. For the second block we have speed equal this expression. You can find it using center of mass frame reference. And the last step to find what is total distance to travel for second block when initial speed is v2. This we can find from energy formula. So we have total kinetic energy going to work done by force of friction. And after that, when we count what is x, we can use all this data to completely count it. That will be this expression. and after we put all numbers we will get around 1.79, which is answer B. Problems 15 and 16. Solutions for this problem you can find below this video on the description. The following figure is used for questions 15 and 16. A small block of mass small m is moving on a horizontal table surface at initial speed v0. It then moves smoothly onto a sloped big block of mass big M. The big block can also move on the table surface. Assume that everything moves without friction. Question 15. A small block moving with the initial speed v0 moves smoothly onto a sloped big block of mass big M. After the small block reaches the height h on the slope, it slides down. Find the height h. And question 16. Following the previous setup, find the speed v of the small block after it leaves the slope. Solutions. Let's see. First of all, for the question 15, we can do a lucky guess for this height, because block M and M, they have some kind of mass, so it means that when this small block reach the highest position, they will move with the same speed, but this speed will be not zero. It means that this height must depend from masses, and the answers A and E, they don't depend from masses. And now let's compare the three other answers. Suppose that big M has a huge mass, so it means that after interaction it will almost not move. It's like motion of small block on the immovable other block. So it means that here we can use regular energy conservation and find what is the height of this small block, because it will not move, not vertically, not horizontally on the very top. So it means that here we have an answer that h must be equal v0 square over 2g, and which is looks like C is a correct answer, because for very big M, this answer is going to v0 square over 2g. But let's do it correctly. So we have to write equations for momentum conservation and for energy conservation. For momentum conservation we have this expression. We have initial momentum, which is m small multiplied by v0, that's equal m small plus m big multiplied by speed of center of mass, because in the highest position they have the same speed. That will be speed of center of mass. From here we can find what is the speed of center of mass. That will be this expression. Now let's write energy conservation. For that we have formula. Initial kinetic energy of the first block, 1/2 m v0 square. That's equal potential energy for this block, mgh, plus kinetic energy for these two blocks, which is 1/2 small m plus big M multiplied by v center of mass square. And now we can count what is height h. This is the calculations. We have mgh equal 1/2 m v0 square minus this one, which is 1/2 m plus m v center of mass square. Now we can insert expression for the center of mass, and finally we will get this answer. And now we can get the answer. H equal V0 square over 2G multiplied by big M over small m plus big M, which is answer C. This is the same as we mentioned before. Now let's do chance 16. Following the previous setup, find the speed v of the small block after it leaves the slope. Now we can mention that this interaction between a small block and big block, that's the same as absolutely elastic collision. Only difference that for absolutely elastic collision we have instantaneous collision for a very short time, but we are not losing energy and momentum. Here interaction is going in a time, but result will be the same. We still have energy conservation and momentum conservation. And like for absolutely elastic collision, they will move out of each other. So we can use the same logic as for absolutely elastic collision. And remember that for such kind of collision we can use approach of center of mass. And we already found what is the speed of center of mass. That's this one. And if we go into this frame of reference of center of mass, in this frame, small block and big block, they are coming to each other with some kind of velocities. But after collisions, these velocities just change the sign, and they will go back with the same amount of velocity but a different sign. And let's count what happened here. So now we can find what is the speed of this small block in the new frame reference of center of mass. That will be this expression V0 minus speed of center of mass, which is big M over small m plus big M V0. After absolutely elastic collision, this velocity just changed the sign. So we can write this one. That will be velocity of this small mass after collision. And now we have to return to our initial frame of reference. So it means that for that we need to add to this velocity of center of mass. So that will be this expression. And now, because mass big M greater than small mass, it means that small block going to the left in a negative direction. But the question is about speed of this block. So we just need to neglect this negative sign, and answer will be E, big M minus small m over small m plus big M multiplied by V0. That's the answer. Problem number 17. Solution for this problem you can find on the reference below this video. 4 masses M are arranged at the vertices of a tetrahedron of side length A. What is the gravitational potential energy of this arrangement? Solution. For 2 masses we have this equation. Potential energy of interaction for 2 masses equal negative g m square over A. And here for 4 equidistant masses we have 6 pairs of interaction. So it means that we have potential energy equal just negative 6 g m square over A. That's the result, D. Problems number 18 to 20. Solutions for these problems you can find below this video in the description. The following graph of a potential energy is used for questions 18 through 20. This one graph. Problem 18. Which of the following represents the force corresponding to the given potential? Solution. We know that force equal this expression, negative delta U over delta X. And now let's see what do we have on this graph. From the left to negative 10, we have force equals 0. From negative 10 to 0, that will be negative by negative 10 over positive 10, which is positive 1. So that's 1 Newton. For same reason, this from 0 to 10, that will be negative 1 Newton. And from 10 to 15, that will be 0. So totally we have 0, 1, negative 1, 0. And using this presented graphs, we see that only graph E exactly corresponds to this force distribution, 0, 1, negative 1, 0. So E is correct answer. Problem number 19. Consider the following graphs of position versus time. These three graphs. Which one is correct? Solution. Let's investigate all three step by step. On the first graph, we have position is constant, that's 15 meters. And if we look at this graph, we have on 15 meters, force is 0. So it means that if we have an object which is not moving, it will not move at all. And graph 1 is correct. On figure 2, we have position is always negative 5. And in this position, we have force equal 1 Newton. So it means that our object must move with some kind of acceleration. But we see that it's not moving at all. So it means that second graph is not correct. And on graph 3, we have motion from 10 meters to 15 meters with a constant speed. If we look at this graph, we have from 10 to 15 meters, force is 0. It means that the object is moving without acceleration. And this graph is correct. So it means that correct answer are first and third graphs, which is D, correct answer. Problem number 20. Consider the following graph of position versus time, which represents the motion of a certain particle in the given potential. What is the total energy of the particle? Let's see. Solution. This particle moving between negative 5 and positive 5 meters. So it means that in points 5 and negative 5 it has maximum potential energy and 0 kinetic energy. So it's moving between this and this point. So it means that in point 5 or negative 5 it has 0 kinetic energy and potential energy equal negative 5 joules. So that's the answer. Negative 5 joules, which is A. Problem 21. Solution for this problem you can find below this video in the reference. The gravitational self-potential energy of a solid ball of mass density ρ and radius r is E. What is the gravitational self-potential energy of a ball of mass density ρ and radius 2r? Solution. From dimensional analysis, we can find that this self-potential energy equal to this expression, where beta is some kind of unknown coefficient multiplied by g m square over r, which by dimensional analysis it has a dimension of energy. Here we don't need to know exactly what is this coefficient beta, because we just need to find how is energy depend from mass and radius. Instead of mass, we can put here volume multiplied by density, and we have this expression. Finally, we see that self-potential energy proportional to r power 5. It means that if we increase radius twice, energy will increase 32 times. So that's the solution. And the coefficient beta could be found using integration, and that will be 5 over 3. But again, I can mention that in this problem we don't need to memorize this coefficient. Problem number 22. Solution for this problem you can find below this video in the description. A balloon filled with helium gas is tied by a light string to the floor of car. The car is sealed so that the motion of the car does not cause air from outside to affect the balloon. If the car is traveling with a constant speed along a circular path, in what direction will the balloon on the string lean towards? Solution. In this problem, the best way probably is to move to non-inertial frame of reference, which is connected to car. And because this car is moving by a circular path, we have inside of this car centripetal acceleration for any body. So it means that we have to add a frictional force acting on any body inside the car with the frictional gravitational acceleration A. If here is our car and point O is a point of rotation around this car, inside of this car we have force of gravity G and the frictional gravity A going outside of point O, and net gravity will go to this direction. And because our balloon floating in air, which is heavier than helium gas, so that will be buoyancy force going outside of this buoyancy force, which is going opposite way to gravity force. It means that balloon will go this way, which is answer D on this picture. And correct answer is D. Problem number 23. Solution for this problem you can find below this video in the description. Two streams of water flow through the U-shaped tubes shown. The tube on the left has a cross-sectional area A, and the speed of the water flowing through it is V. The tube on the right has a cross-sectional area A0 equal 1/2 A. If the net force on the tube assembly is 0, what must be the speed V0 of the water flowing through the tube on the right? Neglect gravity and assume that the speed of the water in each tube is the same upon entry and exit. Solution. Here we can use second Newton law. It means that left tube and the right tube, they create the same force on each other during this water flow. It means that in any small period of time delta t, the change of momentum in left tube the same as change of momentum in right tube. And we can write this equation that delta P1 equal delta P2. Now let's rewrite this equation in form of this one. Suppose that speed of water on the left is V1, and we have mass dm1, which is flowing for time delta t through this pipe. So it means that here we had momentum v1 delta m1, and after time delta t we have momentum negative v1 multiplied by dm1. So total change of momentum in this pipe will be 2v1 multiplied by delta mv1. For the same reason, we have the same expression for right pipe. So we have that's equal to 2v2 delta m2. Now let's represent what is delta m1 and delta m2. We have delta m1 equal cross-sectional area in the left pipe multiplied by dx1, which is distance which mass dm1 flowing in this pipe, and multiplied by rho, which is the density of water. Here we have a1 multiplied by delta x1, that's delta volume, and this is the expression for this small amount of mass of water. For the same reason, we have delta m2 equal area 2 multiplied by dx2 multiplied by density of water, rho. So now we can insert this expression for dm1 and dm2 in this equation, and we will get this expression. Here now we can instead of dx1 put here v1 multiplied by delta t, and instead of dx2 we can insert v2 multiplied by delta t. So we have this expression, and now we can cancel several things. We have delta t and rho cancelled for both sides, and instead of a1 we can put a, instead of a2 put 1/2 a, and finally we have this equation. And from here we can find what is v2 compared to v1. This is the answer. So answer is C, correct. Problem number 24. Solution for this problem you can find below this video in the reference. A uniform circular disk of radius r begins with the mass big M about an axis through the center of the disk and perpendicular to the plane of the disk. The moment of inertia is I0 equal 1/2 mr square. A hole is cut in the disk as shown in the diagram. In terms of the radius r and the mass m of the original disk, what is the moment of inertia of the resulting object about the axis shown? Solution. So first we can represent full moment of inertia of this disk, this whole disk, like this. I0, that's our original moment of inertia, 1/2 mr square. I1, this is the part of this disk with the hole, and the I2, that's the moment of inertia of this part around the center of original disk. So now we need to count what is I2 to find what is I1. Using a parallel axis theorem, we can find that I2 equal 1/2 mr square plus mr square, where m small, that's the mass of our this new small disk, and the small r, that's the radius of this small disk. But m small equal m big over 4, and the small radius equal big radius over 2. So this is how to count what is I2 in terms of big M and the big R. That will be this expression, 3/32 big M big R square. And finally we can count what is I1 of this part of disk with the hole. That will be 1/2 minus 3/32, which is 13/32 mr square, which is correct answer B. Problem number 25. Solution for this problem you can find below this video on the reference. Spaceman Fred's spaceship, which has a neglectable mass, is in an elliptical orbit about planet Bob. The minimum distance between the spaceship and the planet is r. The maximum distance between the spaceship and the planet is 2r. At the point of maximum distance, spaceman Fred is traveling at speed v0. He then fires his thrusters so that he enters a circular orbit of radius 2r. What is his new speed? Solution. Of course, we can solve this problem using regular energy conservation and angular momentum conservation in this problem. So first we can find what is the speed of for circular orbit of this spaceship. This is just a regular formula you can get from equation that force of gravity equal to centripetal force. And after that we can write equations for angular momentum conservation and energy conservation. Here v0, that's speed in the furthest point, original speed, and v1, that's speed of the spaceship in the closest point. After that we can express v1 through v0, put it in this equation, find what is v0 in terms of g m over r, and use this expression. But this is the long way. We can do a shortcut. We can write equation for total energy, which is kinetic energy minus gravitational potential energy for circular orbit, and that will be negative 1/2 gmm over radius, which is in our case 2r. But this formula actually could work not only for circular orbits but also for any elliptical orbit. Let's rewrite it. So total energy for elliptical orbit equal negative 1/2 gmm over A, where A it's the size of big semi-axis of this ellipsis. That could be proved by calculations, but we can use this as our exceptional knowledge. And now we can just write simple equations. First, we already found that v square equal gm over 2r, where v is our speed we need to find. But for elliptical orbit, we have total energy equal negative 1/2 gmm over 3/2 of big R, half of this big axis. But from the other hand, that's equal to kinetic energy in this furthest point plus potential gravity energy. And from here we can find what is V0 square. So from this formula we can find that V0 square equal 1/3 gm over R, and using this expression for V square, we have that it's equal to 2/3 V square. And from here we can find that the V equal just square root from 3/2 of V0, which is correct answer A.